Welcome to today's Explainer. Today, we're basically acting as planetary detectives. We're going to dive right in and uncover the dramatic and, honestly, kind of tragic geological transformation of Mars. This is a true planetary saga about the deep history and the completely lost habitability of a world that somehow went from being a wet, vibrant place to a totally dry, frozen desert. Okay, picture this. It's roughly 3.7 billion years ago, and you're looking at a scene that seems incredibly like ancient Earth, but it was actually playing out right next door. A violent flash flood picks up this massive boulder. It carries it rapidly downstream and ultimately deposits it into a vast 45-kilometer wide crater lake, a crater left behind by an ancient asteroid impact. This isn't science fiction at all. This is a literal snapshot of Mars's deep past, back when it had huge bodies of liquid water, a protective atmosphere, and a much warmer climate. But, as we look at that little red dot in our night sky today, we know those rivers and lakes are long, long gone. So, this brings us to the ultimate mystery we're solving today. We are uncovering the timeline and the actual mechanical processes of how our neighboring planet completely lost its habitability. How exactly does a bustling blue water world turn into a desolate rock? Part 1. The Martian Crime Scene. To figure out what happened, we really have to start our investigation right at the crime scene itself, modern Mars. It's a barren world, appropriately named by ancient cultures after the Roman god of war because of that foreboding reddish tinge. But as our telescopes and eventually our amazing rovers got a closer look, the reality of this world proved way more extreme than any ancient myth. Today, the red planet is unimaginably frigid. We're talking about an average surface temperature hovering around a bitter -80 degrees Fahrenheit. It's just way too cold for liquid water to exist on the surface for any meaningful amount of time. So whatever water is actually left is mostly locked away in polar ice caps, mixed up with solid carbon dioxide. And this dead planet, it's a world of absolute extremes when it comes to geology. I mean, it houses Valles Marineris, this colossal canyon that's 5,000 kilometers long and 10 kilometers deep. To put that into perspective, that would make our Grand Canyon look like a minor pothole. Right alongside it is the Tharsis Bulge, which is home to Olympus Mons. This massive volcano is 25 kilometers tall. That is literally 3 times the height of Mount Everest. It's the absolute tallest peak in the entire solar system. On top of all that, it is completely suffocating. Looking at the breakdown of the modern Martian atmosphere, we can see it's composed of 95% carbon dioxide. But the real kicker here is its density. It is only about 1% as thick as Earth's atmosphere. It completely lacks the greenhouse effect it would need to retain any heat, leaving absolutely nothing but freezing temperatures and massive, wind-swept dust storms that can just blanket the whole planet in a pink haze. Part 2. Echoes of a Blue World. But here's the thing. Mars wasn't always this desolate rock. The rocks on Mars are actually speaking to us, and they're telling a story of a blue world. Our robotic rovers and orbiters have mapped out these unmistakable features. We're talking ancient river deltas, winding valleys, and hydrated minerals, which, by the way, only ever form in the presence of liquid water. In fact, scientists estimate that a massive ocean covered 19% of the Martian surface. That's roughly the area of our entire Atlantic Ocean. The northern lowlands of Mars are particularly fascinating here because they really appear to have been a massive ancient ocean bed, potentially holding even more water than our Arctic Ocean. So the crucial takeaway here is this stark contrast. Ancient Mars shared a very similar trajectory with early Earth. Both formed around 4.6 billion years ago from clouds of dust and debris. Both had active, molten inner cores of iron. Both had thick atmospheres, warmth, volcanic activity, and flowing water. Basically the primordial soup you need for life. They were essentially planetary twins. Well, at least until something inside Mars went terribly, terribly wrong. Part 3. The Cause of Death. The answers to this catastrophic climate failure don't actually lie on the surface at all. They're buried deep within the planet's core. To understand the actual cause of death, we first need to understand something called the geodynamo effect. Just like Earth, early Mars had an active inner core. The rotating, convecting liquid iron in its outer core generated a powerful magnetic field, or a magnosphere. Think of it as a giant invisible shield extending far out into space, protecting the planet's fragile atmosphere from the harsh, charged particles constantly emitted by the sun. But right here is where the paths of Earth and Mars completely diverge, and it literally all comes down to size. You see, Mars only has half the diameter and 1/10 the mass of the Earth. So, with a lot less pressure crushing down on it, its smaller core cooled down way faster. As that core solidified, it could no longer generate that magnetic field. The geodynamo just shut off, the invisible shield vanished, and the planet was suddenly left completely defenseless against the solar wind. So what's the precise official cause of death here? It's a brutal process called atmospheric sputtering. Without that magnetosphere, the relentless stream of charged particles from the sun just relentlessly bombarded the planet. Over millions of years, these solar winds quite literally stripped the atmosphere away, particle by tiny particle. As the atmosphere thinned out, the planet entirely lost its ability to retain heat. The water either froze into the ice caps, got trapped deep in rocks, or sublimated, meaning it turned directly from solid ice into vapor and simply escaped out into the void of space. Tracing the timeline of this planetary demise gives us a surprisingly clear picture. Mars forms 4.6 billion years ago. Studies suggest that by about 4.2 billion years ago, its magnetic field was already rapidly disappearing. And we actually know from looking at the youngest magnetized Martian lava rocks, which basically lock in the magnetic field as they cool, that the planet's dynamo had permanently switched off by about 3.7 billion years ago. The planet was officially dead. Part 4. The Search for Survivors. With the atmosphere stripped, the oceans boiled off or frozen solid, and radiation constantly bombarding the surface, we have to ask the next logical question. Did anything survive this apocalypse? This is exactly where our mechanical detectives, rovers like Curiosity and Perseverance, come into play. Since 2021, Perseverance has been scouring Jezero Crater. It's an ancient, dried-up lake bed whose delta deposits are absolutely perfect for preserving organic molecules, and they are finding some truly fascinating things. They've discovered a variety of organic molecules trapped in rocks that are over 3 billion years old. Curiosity even detected these seasonal cycles of methane in the thin atmosphere. Now, sure, while these could just be from standard geological processes, it's worth noting that on Earth, methane and organic molecules are the very raw materials and byproducts of carbon-based life. While we certainly haven't found definitive proof of aliens just yet, the evidence funnels us toward 3 mind-blowing possibilities. Option 1, Mars never had life, and geology is just playing tricks on us. Option 2, Mars did have life during its vibrant blue phase, but it completely died out during the atmospheric stripping. Or option 3, and this is the wild one, Mars had life, and highly resilient microbial life retreated down to hydrothermal vents or underground aquifers where liquid water and protection from radiation actually still exist today. To figure this out once and for all, our investigation is dramatically ramping up. Back in 2022, Perseverance started packaging these precious rock samples into titanium tubes and literally dropping them on the Martian surface. In 2028, the European Space Agency plans to launch the ExoMars rover to physically drill into the subsurface to look for those hiding microbes. And most ambitiously, in the early 2030s, a joint robotic mission is going to fly back to Mars, scoop up Perseverance's sample tubes, and blast them back to Earth so we can finally study them in our most advanced labs. Part 5. Why Mars Matters. As we wrap up this explainer, we really have to ask the big, multi-billion-dollar question. Why spend all this effort and money to study a dead planet? Simply put, because Mars serves as a perfect natural laboratory. By studying exactly how Mars lost its habitability, it helps us understand the razor-thin margins of planetary evolution. It teaches us exactly what makes a planet capable of supporting life, which directly refines our search for habitable exoplanets orbiting totally different stars. Furthermore, understanding the resources left behind, like that subsurface water ice we talked about, actually prepares us for the Artemis program and a near future where humanity might use those very resources to establish a sustainable presence there. But beyond the science and the space exploration, looking closely at Mars really holds a mirror up to our own world. I want to leave you with this final, kind of chilling thought to ponder the next time you look up at that little red dot in the night sky. If a planet can lose its entire biosphere, right down to the very last microbe, and if it happened to our planetary twin right next door, could it eventually happen here? Thanks for joining me on this deep dive. Keep asking questions and always keep looking up.